Hello and welcome to our first video in a series of videos on trigonometric identities. We're first going to start off with some basic trigonometric identities and then look at simplifying some more complex trigonometric expressions. So first of all, let's talk about what a trigonometric identity is. It's an equation that is true for all real numbers theta. So this is an example of an identity that we're going to use all the time. Sine squared theta plus cosine squared theta equals 1. You'll have to excuse me. My hand's a little shaky. I'm still not used to making videos on my computer. So let's see why this is true. So if we're looking at a point on the unit circle, x comma y, remember that the cosine of the angle theta would be adjacent, which would be the x value, over the hypotenuse, which would be 1. So the cosine of theta is the x value of the point. So that's true for all points on the unit circle. And then the same thing can be said with the sine of theta. For any angle, sine is going to be the ratio of the opposite side to the hypotenuse. And notice if the point is on the unit circle, the hypotenuse is always going to be 1. So the y value for any point on the unit circle will be the sine of the corresponding angle in standard position. So then if we look at this triangle, we have a right triangle whose legs are cosine of theta and sine of theta, whose hypotenuse is 1. And so the Pythagorean theorem, if we just apply the Pythagorean theorem to this triangle, we get that cosine squared theta plus sine squared theta equals 1. Great, so now what if we wanted to manipulate this Pythagorean identity to make some more Pythagorean identities? So I'm going to take the identity sine squared theta plus cosine squared theta equals 1, and I'm going to divide both sides of the equation by sine squared theta. Now the reason I'm going to do that is because I know that it's going to produce an interesting result here. So if I distribute the sine squared theta to the sine squared theta and the cosine squared theta on the left-hand side, I get 1 plus. Now here I get cosine squared theta over sine squared theta. Remember, cosine theta over sine theta, that is just cotangent of theta. So that's going to be equal to cotangent squared theta. And then 1 divided by sine squared theta, that's just cosecant of theta squared. So I wind up with another sort of version of the Pythagorean theorem in terms of theta and standard position. So I get another Pythagorean identity. Notice these are called Pythagorean identities because they sort of originate from the Pythagorean theorem, from the fact that, you know, the traditional Pythagorean theorem here, if the point was x comma y, this would be x, and this would be y, would be x squared plus y squared equals 1, but we're just representing x and y in terms of the sine of the angle and the cosine of the angle. Okay, so let's make our third Pythagorean identity. Again, we'll just start with the original equation, sine squared theta plus cosine squared theta equals 1, and then this time I'm going to divide both sides of the equation by cosine squared. And I wind up with here, if I distribute the cosine squared theta over the addition here, I'm going to get sine squared theta over cosine squared theta, that's tangent squared of theta, plus cosine squared theta over cosine squared theta is 1, and that equals 1 over cosine squared theta, which is the secant squared of theta. So I've created sort of my third Pythagorean identity. So we're going to use these three Pythagorean identities to simplify trigonometric expressions just by using substitution and sort of doing some algebra. So here we have a trigonometric expression, tan squared theta over the secant of theta plus 1. And we want to sort of simplify this. So I'm going to be thinking about some of the identities that I just proved. So my question is here, can I substitute any other expression for tan squared of theta? Well, if I flash back to the previous screen real quick, I know that tangent squared theta plus 1 is secant squared theta. That would imply that the tangent squared of theta equals the secant squared of theta minus 1. So I'm going to substitute in for tangent of theta the secant squared of theta minus 1. Now the numerator is just a difference of squares. I can actually factor the numerator to be the secant of theta minus 1 times the secant of theta plus 1. It's going to be all over the secant of theta plus 1, and now I can cancel the factor secant of theta plus 1 from the numerator and the denominator, and I wind up with secant of theta minus 1. A simpler version of the expression that I started with, tangent squared theta divided by secant of theta plus 1. So basically, we're just sort of playing some mathematical mind games and trickery here. We're just taking some expressions and then making them look like different expressions. And sort of the techniques that we're using here will become very useful later when we want to apply trigonometry to some more advanced mathematical topics. Being able to substitute expressions and make certain expressions look different, and that's going to be very useful in the future. So let's try another one here. Let's see if we can simplify sine of theta times the quantity tangent of theta plus cotangent of theta. So here, I'm just going to apply sort of the distributive property. So this is going to distribute the sine of theta to both of my terms here. Now, it doesn't seem like I have anywhere to go from here. It doesn't seem like any of the Pythagorean identities will help me. It might seem like I'm kind of stuck. So one useful technique to try when you're manipulating trigonometric expressions is to write expressions in terms of sine of theta and cosine of theta. So I'm going to come down here since I don't have much more room to work across. So I'm going to write the tangent of theta in terms of the sine of theta and the cosine of theta. So tangent of theta is sine of theta over cosine of theta. And cotangent of theta is the cosine of theta over the sine of theta. And I get a cancellation here. So I wind up with the sine squared theta over the cosine of theta by just sort of thinking of this as the sine of theta over 1, multiplying my two fractions together here. Then over here, this sine of theta cancels out with the sine of theta in the denominator here. So I wind up with just a cosine of theta. Now I want to add these two expressions together to see if this simplifies further, but I need to have a common denominator. So I'm going to multiply this cosine of theta by the cosine of theta over the cosine of theta, so that I will have a common denominator of cosine theta. So if I come over here, this will be sine squared theta over the cosine of theta, plus, and I'll have the cosine squared theta over the cosine of theta. Now I have a common denominator here. I can add these two fractions together, and I will get sine squared theta plus cosine squared theta all over the cosine of theta. But hold on a second, the sine squared theta plus cosine squared theta, that equals 1. That's one of my Pythagorean identities. So I'm left with 1 over the cosine of theta. That is just the secant of theta. So this crazy expression that we started with here sine of theta times the quantity tangent of theta plus the cotangent of theta, that's just a really complex way to represent the function, or the expression secant of theta. So we're able to simplify this crazy trigonometric expression to just represent that as just the secant of theta. So these manipulating trig expressions is really powerful because you can take really complex expressions and ideas that are going to come up in all sorts of situations, word problems and whatnot, and sort of parse them down and represent them as simpler functions. So this will be really powerful techniques. These techniques will be... So now it's also useful to think about the graphs of the trig functions in order to come up with expressions that are equivalent to other expressions. So here, let me show you what I mean. Here we have a graph for the cosine of theta. But when you look at this graph is symmetric about the y-axis. Cosine of theta is an even function. So remember what that means. When a function is even, remember if f of x is even, that means that f of x equals f of negative x. So if I apply this to the cosine function, that means that cosine of theta will always equal cosine of negative theta, because cosine is an even function. Now the reason that's useful is that because any time now in the future that I see cosine of negative theta in an expression, I can replace that with the cosine of theta, and vice versa. I could replace cosine of theta with cosine of negative theta. So what about the sine function here? The sine function is an odd function. And remember, the definition of an odd function is that f of negative x equals negative f of x. Remember, we can see that the sine function is odd because it has origin symmetry. For any point you pick on the graph, if you reflect that point about the origin, you'll get a corresponding point on the graph as well. So if I want to apply that idea to the sine function, that means any time that I see the sine of negative x or of negative theta, I could replace that with negative sine of theta. And vice versa, anytime I see negative sine of theta, I could replace that with the expression sine of negative theta. It's also, I can think about transformations of these graphs. Like if I took the cosine graph, if I shifted that point right there, if I wanted to move that point to the origin, so if I shifted the cosine function pi over 2 units to the right, if I applied a horizontal translation, I would wind up with the sine function. So if I took the cosine function, shifted the cosine function pi over 2 units to the right, that would give me the sine function. So that's another identity I can play around with. Like any time that I see the expression cosine of theta minus pi over 2, I can replace that with sine of theta. So you really want to think about the symmetry and all of the shifts for all of the trig functions we've done, and you can come up with some identities on your own, like these three here that I've written down. So there's many more variations that we could play around with the sine function, with the cosecant function, the secant function, tangent and cotangent functions. So we're going to be working with identities for a while, and hopefully we'll find some great uses for applying them in the future.